For this last section of today's lesson, we're going to talk about the arc length of a parametric curve, which is going to be very similar to the arc length around a regular function that we just discussed. We're going to use the same logic. To find the length around this curved space, since we don't have curved rulers, we're going to calculate it by figuring out the length of a lot of straight lines, because those are easier to calculate. The distance I have in blue, marked up here, can be calculated using the Pythagorean theorem or the distance formula, the same way we did it for the last examples. The x distance there would be, what we would call dx, the change in the x distance, and dy would be the change in the y distance. Now, technically, the dx in this case would be negative, but remember, we're going to square it, so that doesn't really matter. And so then this length right in here is d, would be the square root of dx squared plus dy squared, using the Pythagorean theorem or the distance formula, however you want to think about it. And then we would just do the same thing for the next line, and 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 the next line. There isn't exactly a rhyme or reason to where I put those. Okay, so what we're going to do then to add all of those up together is we're going to find the sum of the square root of every dx squared plus every dy squared. And this kind of looks familiar, looks like what we saw in the last example. We're going to do something similar, but remember that this time we're talking about a parametric curve. So both our x and our y, and therefore our dx and our dy, should be in terms of t. So what I'm going to want to do is be able to talk about dx squared and dy squared both in terms of t. So what I'm going to do is rewrite that exact same sum, but I'm going to factor out a dt squared. Well, that's a little bit weird to say. I'm going to factor a dt squared out of something that didn't have dt squareds in it to begin with. But like we saw in the last example, if you pull out a dt squared from dx squared, you're left with dx squared over dt squared. Similarly, we'd be left with dy squared over dt squared. What I've done is undistributed a dt squared. You can see if I were to redistribute that, I would be left with the square root of just dx squared plus dy squared. I haven't broken any rules or anything like that. Well, that square root of dt squared can, of course, be written as just dt outside of the square root, which normally I might put in front, but because we want this to resemble an integral in the end, we're going to put the dt in the back. And then in the radicand, I've got dx squared over dt squared. I might as well rewrite that as dx dt squared. And the same thing, I'll rewrite this as dy dt squared. And so now we're talking about the sum of this square root of dx dt squared plus dy dt squared times dt, some change in t. Well, if I were to do this for an infinitely large number of line segments or an infinitely small change in t, so if I were to stick a limit on this, the limit as dt approaches 0, well, then what we're left with is the definite integral. I'm just going to say, well, we'll say from 0 to 2 pi. We can say that because we know in this case it'll take 2 pi seconds to go all the way around because of the period of those sine and cosine functions. Actually, I'll be more broad here. Forget about 0 to 2 pi. We'll do that in this example in just a second. But right now, I'll just call it the distance, the definite integral from a to b of the square root of dx dt squared plus dy dt squared in respect to t. And that is the arc length. So we'll apply this formula for this example here. We'll see that it works pretty easily in the end. If x is equal to 6 plus 5 cosine t, then dx dt is equal to just negative 5 sine of t. And dy dt, since y is equal to 4 plus 3 sine of t, is equal to 3 cosine of t. Don't really need that. So that means that the overall arc length is equal to the square root, the definite integral from beginning to end, because one loop around will happen every 2 pi seconds, of the square root of dx dt squared plus dy dt squared in respect to t. And for the moment, that's not something that we have the skills to do by hand yet. So we will turn to Desmos, and we can integrate that on Desmos. 0 to 2 pi, the square root of 25 sine squared t plus 9 cosine squared t in respect to t. We see that the overall length is 25.53.